Amid the vastness of space, Saturn stands out with the mesmerizing beauty of its radiant rings, a masterpiece of nature. But behind that beauty lie scientific mysteries waiting to be uncovered. From the tiny ice particles that form the rings to the dynamic atmosphere with wind speeds surpassing every known limit. Detecting and tracking near-Earth objects, NEOs, is a crucial mission aimed at minimizing risks from space threats. To achieve this goal, scientists worldwide have established advanced observatories, most notably the Catalina Sky Survey, managed by the University of Arizona. This is one of the leading global programs in identifying and monitoring objects that could pose a threat to our planet. The Catalina Sky Survey uses modern, highly sensitive telescopes capable of continuously and meticulously capturing images of the night sky. These telescopes take a series of rapid photographs, which are then analyzed and compared to detect objects with unusual movement. While stars appear as fixed points of light, asteroids move faster, leaving distinctive trails in the images. This unique feature helps scientists identify them among millions of celestial bodies. Once a moving object is detected, the next step is analyzing its motion to calculate its orbit. This task requires extreme precision, as even a small error in calculations could lead to inaccurate predictions about the risk of collision with Earth. Scientists use advanced algorithms to determine the asteroid's velocity, trajectory, and impact force, providing the most accurate assessment of its danger. If an object's orbit intersects Earth's and poses a potential collision risk, it is classified as a potentially hazardous asteroid, PHA, and continuously monitored. Beyond the Catalina Sky Survey, numerous other observatories around the world also contribute to this mission, forming a global observation network. Projects like Pan-STARRS in Hawaii and Atlas in multiple locations have strengthened efforts to detect and monitor asteroids. Through collaboration among these facilities, data is shared and analyzed rapidly, ensuring that no dangerous object goes unnoticed. This global network also allows scientists to update information promptly and prepare response measures in emergencies. Over the past few decades, modern observation tools have significantly increased the number of detected asteroids. Advances in telescope technology and data processing software have expanded scientists' reach into deep space, where millions of potential objects remain in motion, hidden in darkness. These discoveries not only enhance humanity's understanding of asteroids, but also deepen knowledge about the origin and history of the solar system. However, challenges remain. Scientists recognize that this mission is never-ending. Space is vast and full of surprises, with new asteroids constantly emerging from hard-to-observe regions, such as areas behind the Sun or the dark zones of the asteroid belt. Furthermore, smaller asteroids, while not capable of causing global extinction events, can still inflict significant damage if they collide with densely populated areas. This necessitates observation systems that are not only more sensitive, but also continuously operational to monitor even small but dangerous objects. Current efforts have yielded encouraging results, but the future demands continuous improvement. Global collaboration, investment in technology, and scientific research will remain essential in protecting our planet from cosmic threats. Asteroid detection and tracking programs, whether at Catalina or other observatories, form the first line of defense, helping humanity proactively face challenges from the vastness of space. Saturn's atmosphere is one of the most extraordinary atmospheric systems in the solar system, not only because of its massive size, but also its complexity and dynamism. The atmosphere is primarily composed of hydrogen and helium, similar to Jupiter. But the weather phenomena on Saturn have unique characteristics, creating a vivid and turbulent natural display. The surface of Saturn's atmosphere is covered by fast-moving cloud bands, divided into multiple layers. These cloud layers contain ammonia and methane, two compounds that play a vital role in creating the planet's striking phenomena. When sunlight hits these compounds, they participate in complex chemical reactions, producing diverse colors such as yellow, orange, and pale brown. These colors are not fixed, but constantly change, reflecting the ceaseless motion and transformation of the atmosphere. One of the most impressive features of Saturn's atmosphere is the wind speed. Winds on this planet can reach up to 1,100 miles per hour, about 1,770 kilometers per hour, outpacing every other planet in the solar system. These powerful winds create massive convection currents, contributing to the formation of the characteristic cloud bands. Convection within Saturn's atmosphere occurs on a grand scale, causing the atmosphere to be perpetually dynamic and producing complex cloud patterns. In addition to its incredible wind speeds, Saturn's atmosphere is known for rare weather phenomena. One of the most notable is the hexagonal storm at the planet's North Pole, a unique atmospheric structure in the solar system. This storm spans about 20,000 miles, 32,000 kilometers, in diameter, with atmospheric flows forming a perfect hexagonal shape. The cause of this shape remains a mystery, but scientists believe it may be related to convection currents and aerodynamic interactions within the atmosphere. Beyond surface phenomena, Saturn's atmosphere serves as a valuable natural laboratory where scientists can study how giant planets form and evolve. The chemical composition, interactions between compounds, and distribution of cloud layers all provide crucial clues about the history of Saturn and the solar system. Chemical reactions within the atmosphere may suggest how primordial materials in the early solar nebula coalesced to form planets and moons. Data from the Cassini spacecraft, during its nearly 20-year mission exploring Saturn, has yielded groundbreaking discoveries about the planet's atmosphere. Cassini not only captured detailed images of cloud layers and gas bands, but also measured factors such as wind speed, chemical composition, and atmospheric temperature. This data revealed that Saturn's atmosphere is constantly changing over time, with complex weather cycles and the emergence of massive storms. Saturn's atmosphere also serves as a comparative model for studying other giant planets within and beyond the solar system. Insights gained from Saturn can be applied to unravel the atmospheric structures of other gas giants, such as Jupiter, Uranus, and even exoplanets. This broadens our understanding of how gas planets form, evolve, and interact with their environments. In summary, Saturn's atmosphere is not only a breathtaking natural phenomenon, but also a treasure trove of scientific information. With features like astonishing wind speeds, intricate cloud layers, and rare weather events, Saturn continues to captivate astronomers and the public alike. Studies from Cassini and future space missions will continue to unveil new secrets, helping us better understand this planet and its place in the overall picture of the solar system. Both Saturn's magnificent rings and its dynamic atmosphere play vital roles in unraveling the secrets of the solar system. They are not merely stunning astronomical phenomena, but vast natural laboratories that help scientists study how planets and large planetary systems form, evolve, and function in space. Saturn's rings, composed of millions of ice and rock particles, act as a record, preserving information about the planet's formation history. These icy rings, possibly remnants of a moon or icy object destroyed by Saturn's strong gravitational pull, hold clues about the processes of planetary formation during the early solar system. By studying the structure and chemical composition of the rings, scientists can gain a deeper understanding of how gravity influences the distribution of matter in space and unravel the mechanisms that led to the emergence of planets and moons. Far from being passive formations, the rings interact closely with their surroundings, particularly Saturn's atmosphere. Ice particles from the rings frequently fall into the atmosphere, triggering unique chemical reactions. This process not only alters the atmospheric composition, but also contributes to changes in the ring's structure and characteristics over time. This phenomenon raises intriguing questions about the interaction between a giant planet's components and how these interactions impact the overall evolution of a planetary system. Saturn's atmosphere, with its layered clouds and remarkable wind speeds, vividly demonstrates the dynamism of gas giants. Weather phenomena on Saturn, from powerful convection currents to the unique hexagonal storm at the North Pole, provide insights into how energy and matter circulate within a gas planet's atmosphere. These studies not only shed light on Saturn, but can also be applied to understand the atmospheres of other gas planets, including exoplanets outside the solar system. Saturn's significance lies in its ability to reveal universal principles governing planetary systems. Its rings and atmosphere provide unique insights into this planet, while expanding our knowledge of how other planets in the universe operate. For example, studying how ice and dust particles in Saturn's rings interact with its atmosphere has offered valuable perspectives on the role of such materials in forming atmospheres on other planets. Data from the Cassini spacecraft has led to groundbreaking discoveries about the interaction between Saturn's rings and atmosphere. One of the most significant findings is the flow of material from the rings into the atmosphere, a process that can affect both structures over time. Understanding this mechanism not only helps scientists predict Saturn's evolution, but also provides a model for studying other gas giants in the solar system and beyond. Research on Saturn goes beyond understanding a single planet. It opens new doors in exploring the universe. Saturn serves as a window into deeper insights about how planets form, interact, and evolve in harsh cosmic environments. By analyzing its rings and atmosphere in detail, scientists can uncover universal laws applicable to other planetary systems, including distant ones where life may exist. In conclusion, Saturn's rings and atmosphere are not only defining features of the planet, but also invaluable scientific tools for deciphering the history and dynamics of the solar system. With its spectacular beauty and ceaseless complexity, Saturn remains an inspiration and a leading subject of research, bringing us closer to understanding our place in the vast cosmos. On Saturn, the second-largest gas giant in the solar system, weather is not just about powerful winds or its radiant atmosphere. It encompasses massive and mysterious storms, from the perfectly hexagonal phenomenon at its North Pole to the great white spots that envelop the planet. These phenomena not only captivate observers, but also astonish scientists with the complexity of this unique world. One of Saturn's most unusual and remarkable phenomena is the hexagonal storm at its North Pole, a unique atmospheric structure in the solar system. Unlike traditional circular storms seen on Earth or other planets, this storm has a perfectly hexagonal shape, with 6 equal sides extending thousands of kilometers. Its size is truly impressive, with a diameter larger than Earth, making it one of the most striking astronomical phenomena ever observed. This phenomenon is not only remarkable for its shape, but also challenges our understanding of aerodynamics and planetary weather. The hexagonal storm is maintained by extremely strong jet streams circling Saturn's North Pole. Scientists believe that the combination of the planet's rapid rotation and convective currents within the atmosphere creates this distinctive shape. With wind speeds reaching up to 320 kilometers per hour, the jet streams not only rotate, but also follow a defined trajectory, forming sharp 6-sided patterns that create the nearly perfect hexagon. This phenomenon has not been observed on any other planet, highlighting the unique dynamics of Saturn's atmosphere. Beyond its distinct shape, the hexagonal storm is also fascinating for its seasonal color changes. Data from the Cassini spacecraft shows that during winter, the storm appears pale blue, but as sunlight returns in summer, it shifts to a yellowish hue. This transformation is thought to result from chemical reactions in the atmosphere. During winter, with the absence of sunlight, methane-containing clouds are less disrupted, leading to the characteristic blue color. Conversely, in summer, sunlight triggers chemical reactions among atmospheric compounds, producing a hydrocarbon haze that changes the storm's color. This not only illustrates the dynamic nature of Saturn's atmosphere, but also raises intriguing questions about how light and temperature influence the atmospheres of gas planets. The hexagonal structure of the storm not only fascinates scientists, but also challenges traditional aerodynamic theories. Current simulation models have attempted to replicate this phenomenon, but have yet to fully explain the specific cause of the hexagonal shape. Some studies suggest that aerodynamic oscillations within powerful jet streams can create hexagonal patterns under certain conditions, but Saturn remains the only planet where such a phenomenon has been directly observed. Studying the hexagonal storm also provides new insights into the mechanisms governing giant planets. Phenomena like this demonstrate the complexity of Saturn's atmosphere and broaden our understanding of dynamic processes within the solar system and distant planetary systems. Data collected from the hexagonal storm has helped scientists understand how energy and matter are distributed within the atmosphere of a giant planet, providing a foundation for studying other planets like Jupiter, Uranus, and even exoplanets. Furthermore, the hexagonal storm exemplifies the interaction of natural forces, from planetary rotation and atmospheric convection to the impact of sunlight. This phenomenon underscores that planetary atmospheres are not static systems, but dynamic and complex machines, constantly evolving with time and environmental conditions. In conclusion, the hexagonal storm at Saturn's North Pole is not just a visually stunning natural occurrence, but also a compelling scientific mystery. From its perfect shape to its seasonal color changes, this phenomenon raises new questions about aerodynamics and planetary weather. With discoveries from Cassini and future research, the hexagonal storm will continue to symbolize the complexity and diversity of the solar system while challenging scientists to uncover the deeper secrets of this remarkable planet. Roughly every 30 years, Saturn witnesses a spectacular weather event: massive storms known as Great White Spots. These are not mere white clouds, but intense storms of immense scale and power, far surpassing any weather phenomena on Earth. With their enormous size, each storm can cover an area comparable to a continent on our planet, creating a breathtaking spectacle when observed from space. The Great White Spots originate from a small point in Saturn's atmosphere, where powerful plumes of hot gas rise from the planet's interior. From this origin point, the storm rapidly grows and spreads outward, forming dense and complex white cloud systems. These clouds can blanket much of the planet's surface, dramatically altering Saturn's atmospheric appearance during the storm's duration. Once formed, these storms can persist for several months, causing significant changes in the upper atmosphere. What makes the Great White Spots particularly fascinating is not just their scale, but also how they reveal the dynamics of Saturn's atmosphere. Scientists believe these storms are driven by interactions between atmospheric layers. When hot gases from the planet's deep interior rise and collide with cooler upper layers, they create intense atmospheric instability. This process not only generates the storms, but also drives atmospheric circulation, altering cloud structures and temperatures across the planet. Data from the Cassini spacecraft, one of the most significant missions to explore Saturn, has provided detailed insights into the great white spots. Researchers estimate that these storms can release an immense amount of energy, equivalent to millions of tropical storms on Earth. This energy release not only transforms the atmospheric layer where the storm occurs, but also affects the entire planet, influencing wind speeds, temperatures, and cloud structures. The great white spots also offer profound insights into how the atmospheres of gas giants function. These phenomena show that Saturn is not a static planet, but a dynamic system where internal processes are constantly interacting and influencing one another. Studying these storms not only enhances our understanding of Saturn, but also sheds light on similar processes in other gas giants within the solar system, such as Jupiter and Uranus, as well as exoplanets outside it. Additionally, scientists are intrigued by the regular cycle of the great white spots, which occur approximately every 3 decades. This periodicity suggests an internal rhythm in the planet's activity, possibly linked to how energy is stored and released within Saturn. This cycle also raises questions about how factors like temperature, pressure, and gravity influence the formation and development of large-scale weather events. The awe-inspiring sight of the great white spots captivates astronomers and opens up exciting research opportunities. Understanding these storms could help build more accurate models of atmospheric behavior on gas giants, improving our ability to study space weather. Moreover, this knowledge can be applied to investigate similar weather phenomena on other planets, especially exoplanets with complex atmospheric structures. In summary, Saturn's great white spots are not only remarkable astronomical phenomena, but also keys to deeper exploration of the workings of gas giant atmospheres. With their colossal size, immense energy, and profound impact, they vividly demonstrate the complexity and dynamism of the solar system. Ongoing studies of these storms will continue to provide fresh insights, further illuminating the hidden mysteries of Saturn and other gas giants in the universe. Saturn's atmosphere is a dynamic system, showcasing the interplay of rapid rotation, strong gravitational forces, and external cosmic influences. With a rotation period of just about 10.7 hours, remarkable given the planet's immense size, Saturn has one of the most active atmospheres in the solar system. This rapid rotation not only shapes the overall structure of the atmosphere, but also drives powerful winds and unique weather phenomena. One of the most striking features of Saturn's atmosphere is its extremely strong winds. Wind speeds can reach up to 1,100 miles per hour, about 1,770 kilometers per hour, far exceeding those of any other planet in the solar system. These supersonic winds not only create distinct cloud bands, but also play a critical role in sustaining large-scale atmospheric phenomena, such as the famous hexagonal storm at the North Pole or the periodic Great White Spots. These phenomena highlight both the dynamic nature of the atmosphere and the complex mechanisms driving a gas giant's operation. The dynamism of Saturn's atmosphere is also influenced by intricate interactions among astronomical factors. The planet's strong gravity creates a stable yet ever-moving atmospheric field, while solar winds and cosmic radiation contribute to changes in atmospheric layers. These factors affect the formation of weather phenomena and determine how energy circulates within the atmosphere. Convection currents, temperature differences among cloud layers, and wind speeds work together to create an ever-changing atmospheric environment full of mysteries that science continues to unravel. Another unique aspect of Saturn's atmosphere is its ability to change color with the seasons. Data from the Cassini spacecraft revealed that the planet's cloud layers can shift from pale blue to yellowish hues, depending on the amount of sunlight received. This phenomenon, attributed to chemical reactions in the atmosphere, vividly illustrates the dynamic and complex nature of Saturn's atmospheric system. Studying these changes not only helps scientists better understand Saturn, but also provides crucial information on how factors like light and temperature influence planetary atmospheres. Saturn's atmosphere holds not only intrinsic research value, but also serves as a model for understanding other gas giants across the universe. Discoveries from Cassini have opened new perspectives on how large planets form, interact with their surroundings, and evolve over time. For example, the interactions between atmospheric layers on Saturn can be applied to studying similar phenomena on Jupiter, Uranus, or even exoplanets beyond the solar system. This not only expands knowledge of planets within the solar system, but also helps shape humanity's understanding of other planetary systems. The phenomena in Saturn's atmosphere also contribute significantly to the field of space weather. The energy circulation within the planet's atmosphere can provide reference models for predicting how cosmic factors, such as solar winds or radiation from nearby stars, impact planets. These studies not only serve scientific purposes, but also have practical applications, helping humanity better understand how to protect Earth from space threats. From powerful winds and intricate cloud structures to seasonal color changes, Saturn's atmosphere exemplifies the complexity and diversity of gas giant planets. Each phenomenon in this system offers fresh perspectives and challenges traditional theories of planetary atmospheres and weather. With ongoing research, Saturn remains a vital planet in exploring the universal laws of the cosmos, while providing invaluable knowledge about Earth's place and role in the expansive solar system. The role of moons like Enceladus and Titan in studying the potential for extraterrestrial life. On Saturn, it's not just the icy rings or the powerful atmosphere that amazes us. Its moons serve as gateways to one of humanity's greatest questions. Does life exist beyond Earth? Two remarkable moons, Enceladus and Titan, are not only Saturn's gems, but also the focal points of groundbreaking scientific discoveries about the biological potential within the solar system. Enceladus, a hidden ocean of possibilities. Enceladus, a small moon of Saturn, has become the focus of scientific study due to its unique features and extraordinary potential. Measuring only about 500 kilometers in diameter, Enceladus is much smaller than Earth's moon. However, it conceals a secret that could redefine our understanding of extraterrestrial life. A massive subsurface ocean of liquid water, hidden beneath its thick, icy crust. The existence of this ocean makes Enceladus one of the most important targets in the quest to explore the solar system. This groundbreaking discovery was made possible by the Cassini spacecraft, a collaborative mission between NASA, ESA, and ISA, designed to study Saturn and its moons. During its flybys of Enceladus, Cassini detected icy plumes and water vapor erupting from cracks in the moon's surface, particularly in a region known as the Tiger Stripes. These plumes, resembling giant geysers, shoot into space at high speed and pressure, carrying ice particles, water vapor, and gases from the moon's interior. Chemical analyses of these plumes have revealed the presence of critical organic compounds, including methane and hydrogen, considered building blocks of life. Particularly, hydrogen, a common product of chemical reactions between water and rock at the ocean floor, suggests the possibility of hydrothermal activity beneath Enceladus's icy crust. Scientists have compared this phenomenon to Earth's deep-sea black smokers, where extreme heat and chemical energy sustain ecosystems in hostile environments. This raises the tantalizing possibility that Enceladus's ocean could harbor a similar ecosystem, teeming with microorganisms or primitive life forms. Thanks to Cassini's findings, Enceladus has quickly emerged as one of the solar system's most promising candidates for hosting life. The combination of liquid water, a prerequisite for life as we know it, and chemical energy from hydrothermal reactions creates a potentially habitable ecosystem. This leads scientists to ask whether life exists in the hidden depths of this icy moon. If the answer is yes, it would mark a monumental shift in our understanding of life's prevalence in the universe, reshaping how we view planets and moons as potential homes for life. Moreover, Enceladus serves as a natural laboratory for studying potential biological conditions in extreme environments. Cassini's data has enabled scientists to develop predictive models of the ocean's chemical composition, dynamics, and mechanisms that could support life. Understanding how Enceladus operates not only unlocks its secrets, but also provides clues about other icy moons, such as Jupiter's Europa, that may also harbor subsurface oceans. Each new discovery on Enceladus prompts further questions. How deep is its ocean? Are there strong currents or circulatory patterns? What is the exact composition of the organic compounds, and how were they formed? These questions highlight the need for future missions to delve deeper into this fascinating moon. Ideas under consideration include deploying spacecraft capable of penetrating the icy crust to sample water directly from the ocean below. The discoveries on Enceladus evoke both scientific wonder and hope for finding life in the cosmos. If life exists beneath the moon's icy surface, it would demonstrate that life is not a rare phenomenon unique to Earth, but could be widespread in the vast universe. This realization would not only transform our perspective on humanity's place in the solar system, but also propel further space exploration to answer the ultimate question: are we alone in the universe? Enceladus, with its hidden ocean, serves as a reminder that the universe still holds countless mysteries waiting to be uncovered. The secrets beneath its icy crust could unlock new understandings of life and the marvels of space. Titan, methane lakes, and a thick atmosphere. While Enceladus captivates with its subsurface ocean, Titan, Saturn's largest moon, draws scientific attention with an entirely different set of remarkable features. Its thick atmosphere and the presence of methane lakes on its surface. With a diameter exceeding 5,150 kilometers, Titan is larger than Earth's moon and even surpasses Mercury, making it one of the solar system's most intriguing moons. Titan is the only moon in the solar system with a dense atmosphere, primarily composed of nitrogen, resembling Earth's early atmosphere. This atmospheric composition, combined with surface pressure comparable to Earth's, makes Titan an ideal location for studying the formation and evolution of prebiotic environments. However, unlike Earth, Titan's atmosphere also contains substantial amounts of methane and complex organic compounds, creating an environment ripe for exploration. One of the most significant discoveries about Titan came from the Cassini spacecraft, which detected lakes and rivers of liquid methane on its surface. These lakes, concentrated mainly at the moon's north pole, are composed of methane and ethane, organic compounds that remain liquid under Titan's frigid conditions of approximately -179 degrees Celsius. Data from Cassini revealed Titan's unique weather cycle, analogous to Earth's water cycle. Methane on Titan evaporates, forms clouds, condenses, and falls as rain, creating rivers, lakes, and even liquid-filled plains. This is the only weather cycle observed outside Earth, highlighting the striking similarities between Titan and our planet, despite their vastly different chemical compositions. Titan's thick atmosphere not only supports the methane cycle, but also fosters complex chemical reactions, Under the influence of sunlight, methane and nitrogen in the atmosphere react to produce numerous organic compounds, including tholins, large molecules considered precursors to life. On Earth, similar organic compounds emerged billions of years ago and played a crucial role in the formation of early biological molecules. Titan thus serves as a natural laboratory for studying prebiotic conditions in an environment vastly different from Earth. Although Titan's temperature is too cold for liquid water, a key ingredient for life, its liquid methane could function similarly to water on Earth, acting as a solvent for complex chemical reactions. Scientists speculate that methane could support entirely different forms of life, unlike anything we know. While no direct evidence of life on Titan has been found, each new discovery raises hopes of uncovering signs of extraterrestrial biology. Titan's unique features also expand our understanding of how other planets and moons might develop environments capable of supporting life. The presence of a thick atmosphere, organic compounds, and a methane cycle suggests that life could exist in conditions vastly different from Earth's. This insight also raises questions about other moons, like Jupiter's Europa, where subsurface oceans might harbor life. Titan is not only a massive moon with an impressive atmosphere, but also a vivid testament to the diversity of potential environments within the solar system. Every discovery about Titan not only deepens our understanding of this moon, but also broadens the boundaries of science regarding life's existence and survivability in the universe. Titan's geological and atmospheric characteristics offer clues that may hold the key to one of humanity's biggest questions. Are we alone in the universe? With its distinctive features and immense scientific potential, Titan remains a significant research target, offering hope for groundbreaking discoveries in the future. Ongoing studies of Titan will not only enhance our understanding of the solar system, but also provide fresh perspectives on how the universe might support life in diverse environments. Enceladus and Titan, gateways to life's mysteries. Enceladus and Titan, Saturn's two extraordinary moons, provide profound insights into the giant planet while playing pivotal roles in expanding humanity's knowledge of the potential for life beyond Earth. Despite their vastly different environments, both hold significant biological potential, sparking fundamental questions about life in the universe. Enceladus impresses with its subsurface ocean, hidden beneath a thick, icy crust. Scientists have uncovered evidence of this ocean through icy plumes and water vapor captured by the Cassini spacecraft. These plumes carry not only water molecules, but also methane, hydrogen, and organic compounds, ingredients that could sustain life. Hydrothermal reactions occurring at the ocean floor, akin to Earth's deep-sea black smokers, create an environment rich in energy and chemicals, suggesting the possibility that microorganisms or other primitive life forms could thrive there. Meanwhile, Titan offers an entirely different avenue of exploration with its thick atmosphere and unique methane rivers and lakes. Titan's atmosphere, primarily composed of nitrogen with a significant methane component, resembles Earth's early atmospheric conditions. The lakes and rivers of liquid methane and ethane form a closed weather cycle, mirroring Earth's water cycle. This makes Titan a natural laboratory for studying prebiotic conditions in an environment fundamentally different from Earth's. Titan's atmosphere also harbors complex organic compounds formed from reactions between methane and nitrogen under sunlight. These compounds, potential precursors to life, resemble those that likely appeared on Earth billions of years ago. Studying Titan not only reveals insights into the conditions necessary for life to form, but also raises the possibility of life existing in extreme environments. Future missions, such as Dragonfly to explore Titan or Europa Clipper to study icy moons, aim to build on these discoveries. Advanced spacecraft will analyze the chemical compositions, geological structures, and atmospheric conditions of Enceladus and Titan in greater detail. These missions will not only search for signs of life, but also provide a comprehensive understanding of how these moons function and interact with their cosmic surroundings. The importance of Enceladus and Titan lies not only in their potential to harbor life, but also in the scientific value they offer. They represent two distinct approaches to searching for life, one with a subsurface ocean rich in chemical energy, and the other with a cold surface featuring complex organic chemistry. Researching these moons not only unravels Saturn's mysteries, but also provides models for exploring life on other planets and moons within the solar system and beyond. The discovery of life on Enceladus, or Titan, would mark a monumental milestone in scientific history. It would show that life can thrive in conditions vastly different from Earth's and raise the possibility that the universe teems with diverse life forms. Such a revelation would fundamentally alter humanity's understanding of its place in the cosmos, inspiring further exploration and the search for extraterrestrial life. Enceladus and Titan are not just moons of Saturn. They are keys to unlocking profound questions about life and planetary evolution in the universe. Studying them not only enriches our scientific knowledge, but also instills hope that humanity is not alone in the vastness of space. Each step forward in exploring these moons brings us closer to unraveling the greatest mysteries of the universe and the essence of life itself.